Okay, I'm not going to be explaining a problem from chapter 4 in the genetics homework. The problem. Joan is phenotypically normal but had a child with autosomal recessive disease, cystic fibrosis, from a previous marriage. Joan's father has hemophilia A sex-linked recessive condition where the blood fails to clot properly. Her father has survived due to recent treatment advances. Joan now intends to marry Bill, who is also phenotypically normal, who has a sister Jill with CF. Bill's parents are phenotypically normal and there is no history of hemophilia A in his family. Assume that Joan and Bill do marry and have a child. What is the probability that this child will have CF but will not have hemophilia A? I'm going to be using concepts from chapter 3 as well as chapter 4. So first, I'm going to just give you the overall breakdown of the solution. The probability that this child will have CF but will not have hemophilia A is 1/8, or 0.125. Based on the given data, Joan and Bill's are carriers for CF. So if both the parents are carriers, then 1/4 of their children would have CF, cystic fibrosis, 1/2 are carriers, and 1/4 are normal. And so all of that will equal up to 1. Joan's father has hemophilia A, but Joan may be a carrier or not. If Joan is a carrier, then 1/8 is the fraction that the child will have CF but will not have hemophilia. Okay, so we're going to do a hemophilia Punnett square first. So hemophilia is a sex-linked disease. For the child to have hemophilia, both parents should have an H allele, or the mutant allele responsible for hemophilia. But since Bill's parents have no history of hemophilia, Bill does not have the small H allele. Hence, the probability of Joan and Bill's child to have hemophilia is to not have hemophilia is 1, because both of them would need to have it. And the poem already said, we don't know if Joan has it or not, and we are for sure that Bill does not have it. And so the probability that the child will not have hemophilia is 1. Now moving on to cystic fibrosis. Since Joan is normal, but his child from a previous marriage has cystic fibrosis, then he must be heterozygous. Since Bill's sister has cystic fibrosis, but she is normal, she can be heterozygous or homozygous without the disease-carrying allele, but both would equal the same probability. And the probability of Bill being heterozygous is 1/2. The child cannot have cystic fibrosis if either both parents are not heterozygous or one of the parents is homozygous carrying the disease allele. So the probability of both the parents being heterozygous would be 1/2. We'll do 1 times 0.5, and that equals 1, a half. That equals a half. Probably Bill being heterozygous is a half. Okay. If parents are heterozygous, this is the Punnett square. Big C, little c, big C, little c. That's what heterozygous is. So it'll come out 1/4 would be homozygous dominant, 1/4 would be homozygous recessive, and then we have 2 heterozygous. So big C, big C, big C, little c, big C, little c, little c, little c. So the probability of the child having cystic fibrosis disease would be 0.25, or 1/4. And then the probability, so that would be this. The probability of the child having cystic fibrosis when parents are heterozygous times the probability of the parents being heterozygous. So we already said the probability of the parents being heterozygous was a half. And the probability of the child having cystic fibrosis was 1/4. So you do 1/4 times a half, and that equals 0.125, or an eighth. That's that answer right here. So the probability of a child having cystic fibrosis but not hemophilia would be the probability of the child having cystic fibrosis This is right here. And the probability of the child not having hemophilia, which we already said was 1. So you do 0.25 times 1, that gives you 0.125. So the probability of the child having cystic fibrosis but not hemophilia will be 1/8. And that is how we solve that problem.